What I want to tell you about tonight is one of the most exciting advances in astrophysics in the past couple of decades. It's a new tool that we have that actually goes all the way back to Einstein. And by the time I'm done with tonight, I hope that you understand that Einstein's theories, which really are theoretical in a lot of ways, there's something that a lot of equations involved, but that lens that you're looking through, the talk that I want to give you, is showing you how to make this practical, how we're actually using these, and essentially how you can actually see Einstein's equations sort of carved into the very essence of space and time. And we can see those effects. So the first thing I want to talk about, let's see if I can get my slides, is the fact that in the universe, we see only a very, very small fraction of what exists. So when you look at these gorgeous images of the deep night sky taken by the Hubble telescope, you're seeing thousands and thousands of galaxies. Everything that you're seeing there is a distant galaxy, billions of light years away from us for the most part. But what you're seeing is the tip of the iceberg. That represents much less than 5% of everything that exists. And let me tell you a little bit more about that. And one of the challenges that we have today is that all of our observations of the universe over the past several millennia started with naked eye viewing of the night sky and documenting what we were learning by watching patterns as things changed, understanding how they moved, and interpreting what they meant. That was all coming from visible light. Our very first telescopes looking out at the universe were again from visible light. But over the past couple of hundred years, we've expanded greatly so that we're now gathering light, photons, in just about every energy or equivalently wavelength range available. So we're looking at everything from the very high energy gamma rays to radio waves at the other end of the spectrum. And those have given us incredible new views into the universe and the processes that are going on. Some things you can only see in certain wavelengths of light. But we've expanded even further. We're now gathering particles from outer space, cosmic ray particles that are produced by the sun, that are produced in distant supernovae, that are streaming to us and telling us something about the source of these particles, about what's between the source and what's here on Earth, and trying to piece together an even deeper understanding of the universe from this. We also have instruments out there looking for something like gravitational waves. We haven't actually detected those yet. That's another window into the universe. But I want to talk about something different tonight. Instead of just collecting particles, a different way of seeing things that are otherwise invisible. This is always one of my favorite images. I just love the absolute elegant beauty of a spiral galaxy. The clouds of gas and dust that are illuminated by the stars that dwell within them. And this looks something like our own Milky Way might look if we could view it from the outside. And again, what we're seeing here to a cosmologist represents essentially just the jewel at the very center of a huge sphere of dark matter. So over 90% of this galaxy is in things that we can't see directly. So if we want to understand the universe, we need to go out and find other ways of looking, of seeing, of gathering information. This is a pie chart of what we currently understand as cosmologists about the universe. And I think if you've been coming to some of these lectures, you've been hearing a lot about dark matter and dark energy, and I'm not going to go into too much detail tonight about those, except to show you ways that we're reaching out to try to understand more, to collect more data. But this is very telling. If you look at this pie chart, this is all of the matter and energy, everything that exists in the universe. And normal matter, which is everything that you and I and this planet and every shining star that we can see out there, everything visible, is 5% or less of everything that's in the universe. And we can't even see directly all of the stuff that's made out of what's called normal or baryonic matter, things that are made out of atoms and ultimately protons, neutrons, quarks that form the protons and neutrons. All of that stuff, there's some of it out there that we can't see. It may be too far away or too faint, but in principle might be detectable if we could get close enough to it. But 23% of all the matter, all the stuff out there in the universe, is dark. We can see that it's there. We've got evidence from all across the universe that it's there in having its gravitational impact on the way the universe is shaped, the way things move, the images that we see. But we don't know what dark matter is yet, and perhaps when Glenn comes back from CERN, he'll give you an explanation of dark matter, if he's had a successful semester there. But even more astonishing is that 72% of the universe, we now know, is in something that's not matter of any kind. It's not even the kind of energy that transforms back and forth into matter. It's called dark energy. Because it's dark, we can't see it with even our most powerful telescopes, and it's definitely not matter-like, so we gave it the moniker energy. So that's what we're trying to understand. And the big challenge for understanding the universe right now is to understand what these constituents are, how they're distributed, and what they're doing to the universe that we do see. So here's my very brief history of the universe, starting from the Big Bang 13.7 billion years ago. First of all, I have to stop for a second. Isn't that amazing? We now are putting a decimal place on the age of the universe, and we mean it. I mean, there are error bars that go along with this that I haven't put in there, but 13.7 billion years old. So back in the dark ages when I was a graduate student working with Cyrus, we would say the universe is between 10 and 20 billion years old. Someday far in the future, we may be able to narrow that down a little bit. We got to that answer a lot faster than I think others thought we would ever reach. But at any rate, you go back to the very beginning of the universe, when it was this hot particle soup of everything that existed. And what we're trying to do today, part of the story that cosmology is trying to reconstruct, is how we got from that early period of extremely hot, dense particle soup to the universe of galaxies and clusters of galaxies that we see around us today, and that seems to be expanding at an ever-increasing rate. There are a lot of wonderful mysteries locked in here. But I like to show this slide, because when I show that pie chart and I begin to talk about things like dark matter and dark energy, we can't see it, how do we know that it's there? I think it's really important to at least emphasize that the concept of dark matter and dark energy, the evidence for this, isn't coming from one particular observation or experiment. It isn't an idea. We have been looking and probing the universe from so many different angles. We are looking at, if you look at this, I tried to put in red the ways that we're seeing observations, the ways we're testing this model of a universe that's 23% dark matter, 72% dark energy, and just a sprinkling of normal matter. And we're looking at the universe around us today in all wavelengths of light. We're even using the gravitational lensing I'm going to talk about for the rest of the talk. We're looking at light, we're putting it into its, distributing it into spectra. We are also looking back in time. The further away you look in space, the further back in time you're seeing. The universe itself is a kind of time machine, which is fantastic because we can look at more distant epochs and actually see the universe, including the universe around us today, more or less as it was back at that time. And we're doing this by looking at exploding stars that might be 5 or 7 billion light years away from us. We're looking at faint clouds of gas that will eventually coalesce to form galaxies and the stars within them at even further distances. We're looking all the way back and have begun to see 10, 12, over 12 billion years ago, images of galaxies as they were just first forming. So we're probing almost all the way back to the Big Bang, and we're going further. We have one of the most beautiful images of the universe about 400,000 years after the Big Bang, called the cosmic microwave background, which I suspect you've had a chance to hear about as well. It's a gold mine of information for a cosmologist, but it's showing us a picture, literally a picture of what the universe looked like at that point in time. And we can go even further back from our understanding of particle physics and nuclear physics and begin to understand the processes that went on in that particle soup. And we're looking at it at different points in time and from different observations, ground-based, space-based, all different wavelengths of light, and it all points to exactly the same model of the universe so far. It's just amazing. It didn't have to be that way. But dark matter, dark energy dominate, and the question for us now is how can we go out and probe the universe if we can't see it? And by see it means detect it directly through any telescope of any kind. Now, the dark components of the universe include not only dark matter and dark energy, but they include some really interesting things that we're finding nearby right now, such as planets outside our own solar system. We're limited there by how far we can see the starlight that are hosts to these planets. But we're looking for ways to go even further. And what I want to tell you about today is that Einstein himself, with his equations, left us with a blueprint for an entirely new kind of telescope, something that doesn't detect light in a sense. And there's a really great story that goes with this. So back in 1912, Einstein was working on his theory of general relativity. Special relativity was already done, it was a success, and he did it the way any physicist does, which you start with the simplest problem you can approach. Didn't include gravity, because that was kind of complicated. And now was coming back to add gravity into his theory of relativity. And in 1912, he thought he had it. And anytime a theorist thinks they've got a great new theory, the first thing they do is go find a friend who's an experimentalist and say, if you help me go out and probe this and we discover it, we're both going to be famous forever. So Einstein does this. He goes to Berlin, paid a visit to Erwin Freundlich, and he said, I've got a new theory of space itself and time, and I think the light of a star will bend light coming from something behind it. And our sun is a prime example. The sun is going to bend light from a distant object, and if we can just go out there and see this bending, it's going to be really close to the edge of the sun, we're both going to be down for fame and glory. Now, the only way you can see a star or any light really near the sun is during a solar eclipse, when the light of the sun is blocked. Einstein did send a note, I found in looking over his papers, to the head of Mount Wilson in California at that time and said, do you guys have any way of blocking the sun's light so we can see this? Maybe we can talk about it. And the answer he got back was a rather terse no. This was an observer who wasn't going to waste any time arguing with him about this. So he went back and convinced Freundlich he needed to make these observations during a solar eclipse, which are not really that rare. They happen maybe 7 times a decade, visible from somewhere on the planet Earth. But you have to go to a particular location and time in order to see it. So in 1914, in August of that year, Erwin Freundlich put together his team and headed out to observe the upcoming solar eclipse from the best vantage point, which happened to be the Crimean Peninsula in Russia. Anybody know their history? Yeah, he got there just in time for the outbreak of World War I. Freundlich and his astronomers were captured by the Russian army. They were imprisoned. They confiscated all of their equipment, and they never got to make the measurements. Now, the story has kind of a happy ending because about a month later, they released all of the astronomers. I could never find out what they did to the equipment. But at the time they made those observations, or tried to, Einstein hadn't yet finished his equations, and he was off by a critical factor of 2. If the observations had succeeded, they would not have agreed with his predictions, and the story of general relativity might have had a very, very different ending. I think we would have gotten there eventually, but probably not as quickly. So after the war ends, another astronomer, Sir Arthur Eddington, whom I'm sure you've heard of, sent 2 parties of astronomers out off the coast of Brazil and Africa to make measurements of the eclipse that was happening on May 29th of that year. They were successful, mainly due to a backup telescope, one of the small ones. There are interesting stories there. But the main point is, they came back, announced their findings that agreed with Einstein on November 6th of 1919. And an amazingly quick turnaround on the next day, the London Times had a headline, "Revolution in Science, New Theory of the Universe." And from that moment on, Einstein was synonymous with genius. So what was he talking about with the bending of light, and why was he wrong in the first place? So Einstein's theory of relativity says its most essential features is that space and time are warped by the presence of matter and energy, and matter and energy move around in space as dictated by this warping. So you've got space and time on one side, matter and energy on the other side of his equations. They influence each other. And in fact, this is the rubber sheet that you've probably seen many times. And if we were to put a bowling ball and a baseball on a rubber sheet, they're going to cause a deformation. And what Einstein's saying is this is a 2-dimensional model. In 3 dimensions, there is this warping of space itself. The space, the empty stuff right here in the room around us, is affected by the presence of a massive object, such that it warps space, and anything such as light that's traveling through this space-time, and light's trying to travel in the shortest paths that it can, is traveling through a curved space-time, and it's going to follow those curves and be bent by the light. So that effectively, a massive body acts as a lens. It's going to bend light just like the light is being bent by those model lenses that you're passing around right now. And so this is a cartoon image of what he was saying was going to happen at the eclipse, which is that the sun causes a warp in space, and if there's a star that's right near the edge of the sun but maybe a little behind it, that light is going to be bent, curved around. It won't be a sharp angle like that, but it'll be a curved angle that will come around, and it will appear on Earth as if the stars around the sun have been shifted out of their normal positions. So what you do is you go look at a patch of the sky when the sun isn't there, and you measure exactly where the stars are relative to more distant background stars. You come back and do the same thing when the sun is there, acting as a lens, and what you see is those stars actually shift out from where the sun is and are shifted in the sky, exactly as Einstein predicted.
In the rubber sheet, it looks like a physical bending, and you'll probably cover this later, but how does that physical bending then translate into waves? You know, when we're talking about gravitational waves, that would seem like something that would be pushed out or, you know, caused by this.
Yes, so you've got a good mental image in your mind right now. So if we're talking about gravitational waves, let's say you put the sun, you put this ball on the rubber sheet, and it's creating this deformation. Now take the ball and bounce it up and down like this. What's going to happen? You're going to send ripples of that stuff out into the surrounding rubber sheet, and that's exactly what happens with gravitational waves. So what we're looking for right now with some of the gravitational wave detectors that are out there is for, say, 2 black holes or 2 neutron stars, 2 pretty densely massive objects spiraling around one another and essentially stirring up space-time, just like you might stir up the surface of a liquid, and sending those waves out. So it's a good image.
I read that Eddington actually tweaked his numbers to prove general theory relativity equations. Can you comment on that, please?
Yes, that's an interesting question. So there's been some I don't know if it's papers, but there's been writing that says that Eddington tweaked his numbers, he fudged the data, he didn't quite do it the way a scientist would. The eclipses weren't straightforward. They got clouded out, I think in Africa, I could have this backwards, and the Brazil telescopes, they had a backup 4-inch, so that they knew that the conditions weren't ideal that they were observing from. And I went back and looked pretty carefully at what he presented to the Royal Astronomical Society, and actually I would totally disagree with that. He didn't fudge the data. He said, we have reasons that we know this didn't work pretty well, which is what you do in science. You look at the experiments that you've done, you say, we know that the uncertainties here are affected by this, this, and this one seemed more stable. We've done some tests on it. He presented all the data, and so if you look carefully, I think it's all right. Now, what wasn't presented usually were the error bars that went along with this, and so a more careful statistical analysis by Eddington would have been very helpful, but I don't think you could say that he really fudged the data. But it's an interesting story of how science is done and how the rumors get out. So in 1936, so this is back in 1919, and those notes that I showed you that he wrote up and went to with Berlin actually sketched out pretty much all of the characteristics of gravitational lensing I'm going to be talking about tonight. But in 1936, you can find another notebook where he redoes all of these equations. It's not clear if he forgot that he'd done them carefully before, or he'd done them, redid them again here. What he has here that's different is he's got this factor of 2 right. When he first did his equations, he understood that time would be affected by the presence of a massive object. He hadn't yet got his mind around the fact that space itself could be curved. So as I'm talking tonight, and it's difficult for you to get a mental picture of empty space actually having some shape to it, you're not alone. And it wasn't until he came back and talked with one of his mathematician colleagues who showed him the math to use in curved spaces that he began to understand more deeply that not just time but space would be impacted by the presence of mass. So he's done it correctly here. And this is called a note to Herr Mandel, because what he did was he published the results of this last effort. And it's called Lens-like action of a star by the deviation of light in a gravitational field. So he understands that this is acting like a lens. And he goes on to sketch out the equations for lensing of a star, a distant star by a closer star, and the double images that you saw when you were passing these lenses around, a ring of light, describes all of these things. And then he adds, It's a most curious effect, the production of these rings and multiple images. Of course, there is no hope of directly observing this phenomenon. And he was 100% wrong there. Not only has it been observed, but these equations, these double images are exactly what we're using to probe the dark universe. And there's a little footnote. He also said, in a note to the editor when he submitted the paper, "Thank you for your cooperation on the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." Mr. Mandel was an engineer who kept bugging him saying, "Please publish it, please publish it." So Einstein, in just trying to be nice to somebody, publishes a paper that's changed the direction of astronomy today. So it was a nice note, he was being nice, but it is of little value, it is of immense value. And gravitational lensing is now one of the most important tools we have in all of cosmology and astronomy, and it's absolutely critical and a very important component of every search to understand what dark energy is. What can we do with this idea that you can get rings of light, multiple images, etc.? The fact that you can use space itself, this warping of space as a lens. You can find distant planets. So far, and I just checked this again today because the number keeps going up, there are 809 confirmed planets outside our own solar system. And there are another 2,321 Kepler candidates that we expect probably 90% of those will ultimately be confirmed after more observations. And of those, about 20 of them have been found with something you've probably heard very little about, but using this lensing property, and I'll talk about that in a little bit because it's an interesting story. You can weigh or find out how much matter is in a galaxy or a cluster of galaxies even if you can't see it. You can use it as a magnifying glass and peer into galaxies right after they just began forming. You can test alternative theories of gravity, which is essential in looking at our theories of dark matter and dark energy. You can map the web of matter that we think fills the entire cosmos, and from doing that, you can find the imprint of dark energy. So here is probably one of the only equations that I will show while we're here tonight. And this is just basically if you have a mass m, and you've got light that's traveling past it, and it's about a distance b away at its closest approach, it's going to be bent by that much of an angle. This comes out of basic geometry and Einstein's equation. Exactly what we see depends on how close we are to this massive object and how far away it is from the source of light and how close the light passes to it and how big the object is. So think of that dent in space in the rubber sheet. The bigger the dent, the warp that it makes, and the closer you are to it, the more your path is going to be changed. So when we look out at the universe, if we have a galaxy, and there's a distant bright object in the universe, and it's lying directly behind that galaxy, that square is showing you what you would see through a telescope. You'll see the nearby galaxy surrounded by a ring of light. There's not really a ring of light there, it's just the same as the ring that you saw through the lens I passed around. It's the reason I want you to have this lens. This is something in a subject that's very difficult sometimes to get your mind around that can be very intuitive. We all understand how lenses work. We have glasses, magnifying glasses, telescopes, microscopes, and it's now the difference is instead of being sculpted out of metal or glass or plastic, it's sculpted out of space-time itself. And so that's what we would expect to see. Normally things aren't lined up completely, so if the quasar in the distant universe, some bright source of light, is a little off-center from the foreground galaxy, you won't get a ring, you'll get two images, just like the double images that you saw. And there are all kinds of special effects. So starting with a question mark on the far side as being the basic thing, source of light we're looking at, if I put a black hole directly over that, between me and the question mark, what I'm going to see is a ring of light. If I move it a little off to one side, I get two images, one of them is inverted. And if I just barely bring it out from the side, on the far side of where that question mark is, you can see it gets distorted, stretched out, moved out of the center a little bit. And all of these effects are important. And since Glenn cannot be here in person, I decided to invite him to be my model of gravitational lensing to show that when you see something you don't expect, I actually had a picture of him when he looked like he was about 25 years old. I decided not to show that one, but see me after. If there were a black hole between us, a gravitational lens of some kind, we would know that there was something very different going on here. Now, when we look at something that's a more complicated image, we're looking down, this is the visitor center at NASA in Baltimore. And if I were to put a black hole sort of between us looking down, you could see that the galaxy at the end gets lensed into a ring of light. But also notice what happens to the little images on the side. You'll see them get pushed out from the center, elongated tangentially, and those effects are also very important. Now, the first observation that Einstein said would never happen took a long time. It wasn't until 1979 that the first double quasar was discovered. Astronomers found two quasars, which are essentially black holes in the distant universe that are rapidly and voraciously devouring things around them and giving off huge amounts of light and energy. But this double quasar very closely on the sky, when you look at its light very carefully, it was clear it was not two quasars, but two images of the same quasar. And the first Einstein ring was not seen until 1987. So what do we see when we actually look out at the universe? Here are 8 examples of Einstein rings. So what you're seeing in each one of these, start in the bottom row, second from the left side, because that's the clearest. The bright yellow-white thing in the center is a galaxy, about 2 billion light years away from Earth. The blue ring around it is not a blue ring. It's an even more distant galaxy, another 2 billion light years behind the first, lying directly behind it and lensed into a pure ring of light. This is what I mean by seeing actually the sculpture of space-time, the architecture of space-time. You're seeing it just as if we had taken some kind of rubbing. So space is not just empty, it's got an architecture, a shape, warps and dimples and wonderful structure to it that we can reveal by shining a light through it. And this is what we're seeing. Those are from Hubble Space Telescope. These are some images from a colleague at the University of Chicago from a ground-based telescope where, again, you're seeing these rings and arcs of light that are not really there. If the mass wasn't warping space, they just look like a small blue smudge. And here's an example of this. This is an Einstein, an almost complete Einstein ring. Again, the big image is real. You're seeing in the white is a galaxy. The blue is a more distant galaxy behind it that's been lensed into that shape. And on the side, these are computer-generated images. And what you want to do is you try to make a model of what that lens really looks like. So you start with that white galaxy, and you have to put dark matter around it. And you don't know exactly how it's shaped, but you have a pretty good idea. And you take that and you put it in front of a little blue spot that would be the background galaxy, and you see what you get, and then you iterate back and forth until you get something that looks exactly like what we're seeing here. And in that case, you go back and you say, okay, the top is what the galaxy would look like if it weren't lensed. The second is what the galaxy looks like that's doing the lensing. And then on the computer, that's the image that they get. And we do this in much more complicated scenarios, but this is the basic idea. So if we start in our own galaxy, and this is an edge-on image in the far infrared of the Milky Way, and we look at stars either out from our own galaxy or towards the center of our galaxy, we can actually see this lensing effect happening. So my little cartoon here, this is the artist's conception of a galaxy. We're about 2/3 of the way out in the disk, and we're looking along 2 lines of sight, and let's focus on looking towards that central bulge, a collection of concentrated stars at the center of the galaxy. And if, as we're looking at some of those stars in the center of the galaxy, we're looking at their light and monitoring it, and another star happens to pass between us and that star and line up directly, what you get are 2 images of the background star. Now, because it's such a faint lensing effect when we're talking about our own galaxy, you don't see 2 images, you just see the star get brighter. So what you're seeing on this side over here is that as the star passes by, the star we're looking at seems to get brighter and dimmer again in a very specific way. So that's one way you can find something. You don't have to see the star that's moving in front of us. And everything in space in our galaxy is moving. Nothing stands still. And this is essentially what it looks like. So you're following a field of stars over time in our galaxy. So these squares just represent time progressing forward. And you can see there's a star with an arrow pointing to it that it's one of the fainter stars if it's in the upper left-hand corner. And by the time you get about halfway through, it's the brightest star in the image. And then it goes back to being dimmer again. You've just seen lensing in action. But the cool thing about this I want to talk to you right now is this is how you find planets. So if you have a star in the middle of the galaxy, that's your light source. And then you have another star about halfway between you and the center of the galaxy, that's going to be your lens. So if this star passes between you and this other star in the center, it's going to make it get brighter. But stars, as we're finding, often have planets around them. And so what's happening is this star moves in front of it. You've got a planet that takes the warp in space caused by the star and adds a little dimple onto it. And that little dimple changes the pattern of light that we see. So what you expect to see is, again, this is the brightness of the star. It starts out, it gets brighter and brighter, and then it starts to get dimmer, and all of a sudden there's a little blip, extra spike of lensing, and that's due to a planet. You have to monitor it very carefully, and it's happening over a course of hours. But we actually see this. So here's a real light curve as you're monitoring the star. It gets brighter, it gets dimmer again as we're watching it, and then there's a little peak there that tells you there's a planet. And that planet that you're seeing here is about 5 times the mass of the Earth, at about 2 or 3 times the distance between the Earth and the Sun. The great thing about lensing is its sweet spot, where it's best at detecting planets, is at about the same distance that we are from our Sun. So most of these other 3,000 planets that you're finding are much, much closer to their home stars. So that's point 1 in favor of microlensing or lensing to find these planets. Point 2 is it works better the further away you are. So with this, we're able to find planets that are thousands or tens of thousands of light years from Earth, where almost all of the other planets that have been detected are within a few hundred or at most 1,000 or so light years. So we're probing an entirely different part of the galaxy. And in fact, we've been able to find one of the smallest extrasolar planets so far with lensing. The most distant planet outside our own solar system ever found is over 21,000 light years from Earth, was found using this lensing technique. And then they did something more. Because you're probing and surveying a bigger amount of stars towards the center of the galaxy, you can begin to make some estimates. And basically in January 2012, a group published a paper that based on their lensing results, they're saying pretty much every star in our galaxy has a planet around it. So we've taken it from 3,000. We haven't seen them all yet, but the evidence looks pretty strong that if there are about 300 billion stars in our galaxy, there are probably at least 300 billion planets as well. Magnification. Lensing, when you put a lens in front of it, also can magnify things into view. So jumping gears a little bit, this is an image where you see this long arc in the middle, and again, that's not real, but the circled objects are 2 images of a galaxy that formed only 200 million years after the Big Bang. This is right at the edge of anything we might ever possibly see. And not only does it magnify it into view, we would not have seen this if it weren't lensed, but it also, in some cases, and here's one, this is a cluster of galaxies, the yellow, white in the center, a cluster of galaxies about a few billion light years away, and that big blue arc and the other blue smudges that stand out is actually a single galaxy. So here we've circled the same images, so you're seeing 4 images of the same object, and it's the brightest magnified, it's the brightest lens galaxy that's ever been detected. And it allows us, in this reconstruction that you're seeing down below, to see the star-forming regions in a galaxy that existed 10 billion years ago. So we're actually able to go back and reconstruct how galaxies formed, how the stars in them formed. It's forming stars much more vigorous rate than we are in the Milky Way, but it's a way to probe the early universe that wouldn't be possible without it. So the next big topic, are we out of time? No, okay, is looking for dark matter itself. This is the really cool stuff. So this image, if you look at that pink thing on the side, this was called the Dragon for years before Hubble Space Telescope could see it. Again, it's a couple of images smeared together of a single distant galaxy. And it was first seen as a large arc in 1976, but it took them quite a while to really connect that to gravitational lensing. And people spent a long time trying to explain an arc that was maybe 300,000 light years across. It made no sense, and it shouldn't have, because it isn't an arc 300,000 light years across. It's really a lensed effect. And this distorted image is now being able to see in much clearer view, and this begins to tell us something about the galaxy cluster that's doing the lensing.
I think the blue areas were due to lensing, am I right?
If we go back, let's see.
There.
Yep.
The ones that, all those
They're all
blue
circled,
areas.
yes.
Are you saying then that that cluster of galaxies is acting as a single gravitational locus causing the lensing?
Yes, and I'll show you an image in a minute about what kind of a lens it is. It's a lens, but it's a complex lens. So what we've been seeing up until this point, and the reason you can get some of these really gorgeous images of long arcs and multiple images of multiple distant galaxies, is because, first of all, clusters are the most massive objects we know of in the universe. They're just huge, so they create a huge dent in space-time, but they've got galaxies in them. So you've got one giant lens, in effect, from the galaxy, and then, or from the cluster, and then lots of little lenses from the individual galaxies themselves. So it's a very complex lens, and creates some of the most strikingly beautiful images I've ever seen in the universe.
And the shape of that galaxy then is not the spiral that we see. This is the formation of what will eventually become a spiral.
Yes, and there's been, this is off topic, but there's been some interesting work lately as we've been able to see more and more galaxies early in the universe, to see that galaxies like our own Milky Way, sort of that it sometimes takes them a while, first of all, to settle down into any kind of regular shape, but also then into a spiral shape as well. It's a more mature galaxy. So this is another image, again, of a cluster of galaxies. All of the bright yellow-orange are clusters in a single galaxy. So a cluster can have hundreds or even 1,000 galaxies in it. That's why it's so massive. And all of these galaxies are, again, embedded in a huge sphere of dark matter. So there's not just dark matter around the galaxies. There's dark matter in between all of the galaxies in a cluster. And so what you're seeing in this image, there are 5 images of a single background galaxy that are circled here. And this is one of the first images that they used then to find out exactly what that complex lens looks like. So if you work backwards, just as we did to find that simple galaxy and distant galaxy image, what you get isn't a simple lens, but something that effectively is described by this. So what you're looking at on each axis there is sort of position on the sky. So just look at a patch on the sky, up, down, left, right on one axis, up, down on the other, for example. And those peaks correspond to, there's a mountain there. So this is almost like that rubber sheet analogy, but flipped upside down. So the higher the peak, the more mass that's there, the more warping in space-time. And so the mountain that you see is due to the dark matter in that cluster of lenses, or cluster of galaxies. And then there are 119 individual little spikes in this lens due to the galaxies within the cluster. And it's a stunning image of that's what space-time kind of looks like. There's that amount of warping in there. This image gives you something a little bit different. What you're looking at here, again, a cluster of galaxies, and the brightest one is that bright orange yellow in the center. But you see the thing with spikes on it? I don't know if you can see that there are 4 images, and there's one in the center you can't see. It's a bright white blue, and it's got diffraction spikes on it. So when you see something in an astronomy image that has those spikes on them, it's either a star that's very close. It means it's, as far as the telescope can tell, it's a point source. It's not a spread out source like a galaxy with lots of light. It's just a single point of light. So that's either a star in our own galaxy, or in this case, it's a quasar in a much more distant galaxy. And that quasar is not, again, 4 images or 5 if you count the one in the center. It's a single quasar that's been lensed 5 times over. And in fact, this cluster is such a great lens. What you're seeing is anything with the same letter at the beginning is the same object. So you're seeing multiple images of several galaxies, A, B, C, and the more you learn about the lens, the more you know where to look to find more copies of lensed images. But the Q1, 2, 3, 4, and 5, that's a single quasar. The cool thing about this is, remember that Einstein's equations are not just about space, but about time. So each quasar in the universe is not a single steady source of light. The light varies over time. So it's a little bit brighter, a little bit, and it's sort of a pattern that seems random to us. But you can look for patterns within that intensity change and see, it's almost like listening to a song. And you hear a phrase in this song. And because of the lensing effects and what it's doing to space and time, the light from each one of those images arrives at Earth at a different time. There's 2 effects going on. They're traveling through different paths in space. So the light starts out from the same place, but the one that goes way out here before it curves back is taking a longer path through space. There's another effect. The closer a light path goes to a very deep potential well, the more that light is slowed down momentarily. And when you put it all together, we listen, in effect, to the song that this quasar is singing. And we hear the pattern first in Q1 that you see up there. And then about 2 years later, 780 days, you hear that same phrase, that same song in Q2. 40 days after that, you see it in Q3, and then a few years later in Q4, and we can't get the one in the center. But that's amazing. You're actually not just seeing, but in a sense, hearing Einstein's theories. How do we know that dark matter is out there and it's not something about gravity that we don't know? This I'm going to go through relatively quickly, but it's fun because Glenn is over at CERN right now, and a collider is basically particle physicists doing what they love to do, which is smashing things together at higher and higher speeds and seeing what comes out of the crash, right? Astronomers don't get to do that. You just have to wait and see what's happening in the universe. But every now and then you get lucky, and two galaxies, or in this case, two clusters of galaxies, are going to collide. Everything in space is moving, and if it's close enough and headed towards each other, there are going to be collisions. So there was a cosmic collision that happened about 100 million years ago, and we've got a picture of it. And this is the image. There are two clusters there. It would be hard to pick out, so put some arrows on to show you there's a center of each cluster, and they basically passed through each other. Now, a cluster of galaxies has three main components. The galaxies we talked about. It also has the dark matter halo around each cluster of galaxies we talked about. And it's also got hot gas, some hot gas that gives off X-rays that spread around between all the galaxies. When the collision happens, here's what we expect. You got a cluster here, they crash through one another. The galaxies are so far apart in space that they essentially just pass through the clusters, the galaxies in the other cluster, without anything happening. So they just pass on through. Dark matter doesn't interact with almost anything in the universe, including itself. So we expect the dark matter, halo here, crashes through, it just keeps on going. Gas, on the other hand, you get one cloud of gas here, another cloud of gas here. When it crashes, you get some shock heating and it slows down. It interacts. Anytime you have an interaction, that takes time. So what you expect to see in a cluster collision like this, if there is dark matter, and it's the main component in the galaxy clusters, is that where you find the galaxies at the end of the collision, you should also find the dark matter in that point in space. But the gas should have lagged behind. So this is an optical vision. If we look in the X-ray, we see exactly what we expect. So you see the clouds of hot gas, X-ray emitting gas, associated with each cluster are closer together because they slowed down. They've lagged behind in this collision. And it's called the bullet cluster because you can see almost the sort of the bow front on the one cluster that passed through the other one. Now, if there's dark matter there, what you expect to see is that it should have passed through and be lying on top of where the galaxies themselves are in the optical. And we have a way to find out where they are if dark matter is the most massive component of a cluster, which it is if it exists. And so when we use gravitational lensing to actually see the invisible, to make a map of where most of the matter is, you can see the blue is outlining where the dark matter is, and it lies right on top of where the galaxies are and not where the gas is. If there was no dark matter, the only thing in the cluster would be the galaxies and the hot gas. And we know by studying lots of clusters, there's a lot more mass in that gas than there is in the galaxies. So the mass map should have been over top of where you see the gas. It's not, so it's telling us that changing gravity is not likely to be the solution to all of the evidence we see for dark matter in the universe. Dark energy, on the other hand, is an even more intriguing question. It's predicated on this observation that just won the Nobel Prize last year, that the universe, which has been expanding since the beginning, since the Big Bang, is not slowing down, but speeding up. It's expanding at an ever faster rate. Something has to be fueling that acceleration. And that's something, because we don't know what it is, as I explained before, we're calling it dark energy. We want to know what it is, we want to know how it interacts in the universe, and we want to make sure that this isn't something we don't understand about gravity as well. And a task force that was studying this fantastic new question and challenge in front of us concluded that gravitational lensing, this tool we've been using, offers the greatest potential for constraining dark energy. The question is, how do you search the universe for something that you can't see? It doesn't clump like regular matter, and we don't have any ideas for how to go out and find a piece of dark energy. So there are two things you do. You let the theorists go completely nuts and come up with every theory that they can, and they're very good at that. And then you try to constrain them and bring them back to reality by making observations and seeing what effect does it have on the universe. And there are two things that dark energy does. Dark energy has two major effects. One, it increases the expansion rate of the universe. So the universe is expanding out, and it increases this, and you can see this by looking at how far away things are. It also, because it works in a direction opposite to gravity, gravity wants to slow down the expansion of the universe. Gravity wants to collapse things together. Dark energy is going to fuel the expansion of space, which makes it harder for things to collapse. So it inhibits the growth of things like clusters at later times in the universe when dark energy is the main component. And gravitational lensing can help us find effects, both of these effects, because the lens, as we talked about early on, depends on how much mass is out there, how concentrated it is. Dark energy is going to affect that, and how far away these things are from us, which also dark energy will impact. So dark energy is going to leave its imprint very strongly on something called the cosmic web of dark matter. This is a computer simulation. If you could see the universe with dark matter eyes, this is what we would see when we looked out. A beautiful web of filaments that stretch across the universe, and at the knots is where you would find a cluster of galaxies, for example. We don't see a universe that looks like that. We just see sort of the highlights, the tips of the iceberg that represent the light elements in the universe. So this is looking at the universe. That web at the very earliest part of the universe was pretty evenly dispersed. And as time goes on and billions of years pass, the web gets tighter and tighter until it's the web that we would see today if we could see it. We want to go out and find that web. We want to see what it looks like today, and we want to look further and further away at that web to see how it's evolved over time, because this compression that you saw as these filaments got more and more compact and more sharply defined, dark energy is going to inhibit that. If it's actually stuff that's out there. If it's some kind of new theory of gravity, which we're still looking at very actively for dark energy, it could have very different effects. So we know what to expect if it's some kind of stuff that fills the universe, and we need to go out and look at it. And so we're trying to do that by using the most distant galaxies we can find as sources of light and shine them through that web. And just like taking a flashlight and shining it through a screen, a kitchen screen, we're shining the light of these distant galaxies through the screen of this web, and we want to see how that web distorts the images that we see. It's not going to make double images and beautiful arcs, because the effects are much more subtle. But it will take, and in this image, what you're seeing is these little blue squiggles all started out as flat blue disks, just to represent a typical galaxy in the background. If they're all circular disks, by the time they get to us, they've been stretched and tweaked in different positions, sometimes to sort of line up along the filaments. And by measuring that effect, we can actually detect the dark matter web and begin to understand how it's evolved over time. That's actually started. So this was actually 2 years ago now, the Cosmos survey, which is going out and effectively taking a CAT scan of the universe by detecting these distant galaxies and seeing how they've been distorted by this web of matter, and begin to reconstruct something that doesn't look much like a web yet. We're just beginning this process. The technology is not very good yet. White and green are things that are closer to us. Red and orange are further away. But we're seeing mass. There's no light. There are no galaxies where you see this. This is where the mass is according to this CAT scan of the universe. And this is what we're planning to do in large part with some of the major surveys that are coming up to look for dark energy. And in particular, the Dark Energy Survey, which is one of the largest collaborations to go out and scour the universe for any evidence of the impact of dark energy in a couple of different ways, just saw first light about a week ago. So they've been working on this for at least a decade, and it just turned on in time for this talk tonight, which I thought was nice. It's a challenging thing to go into because you're not dealing with nice little blue disks for distant galaxies. They're all different shapes and sizes, so you only know on average what one should look like. So statistically, you need to look at millions of different distant galaxies in order to really tease out this effect, but we can do it. And this has started. I want to end just by telling you a couple of the latest discoveries that have come out of gravitational lensing. So just about a year ago, these surveys that are looking at stars in the center of the galaxy found about 10 orphan planets, they called them. Planets that are not around any host star. The only way to find them is through some kind of lensing technique. They're about Jupiter-sized planets because the warp in space caused by something Earth-size on its own would be too small to really see unless you know exactly where to look. But by using some survey techniques, you can find that there are free-floating planets, and that's changing some of our understanding of how solar system formed, and maybe these planets were kicked out early in the formation of their own solar systems. A distant cluster of galaxies. So what you're looking at in this image, and this came out, I think, in May or June of this year, there's a cluster 10 billion light years away. It's one of the most distant clusters that we know of. And what you're seeing in this box is a blow-up of what's in the box on the corner. And there's an arc there of an even more distant galaxy somewhere further away than 10 billion years. They haven't been able to pinpoint exactly where it is yet. And what the astronomers who discovered this are saying is that shouldn't be there. There shouldn't be a cluster massive enough in the universe at that point in time to have that strong of a lensing effect. So this is beginning to tell us that some of our ideas aren't quite holding together about how structures formed in the very early universe. And I'm going to end with this image, which I think is beautiful. This is the first detection, published just in July of this summer, of a filament, those threads and filaments that we saw in the cosmic web. You're looking at the big blobs on either end are clusters of galaxies. And lensing of over 40,000 galaxies by this mass in between, that bridge that connects them, is a filament of dark matter. And we've seen for the first time, and it's actually the 222 is closer to us just a little bit than the other one. So we're almost looking down the barrel of that filament, which makes its lensing power much more effective. But we're actually beginning to see that cosmic web. And it's a very exciting time in the study of the universe. Thank you.